Yeah, so CONIKS is a key verification system for end users that is practical and integrates with existing secure messaging applications. Billions of users today rely on online services for their sensitive communication. As these users learn about the wide variety of threats to the security and privacy of their communication, their demand for end-to-end secure communication is growing steadily. To meet this demand, an increasing number of existing and new communication service providers are adopting end-to-end encryption. And they have realized by now that key management is difficult for the vast majority of users. But one important problem that remains largely unsolved is how users establish trust. Trust establishment is about how the communicating parties learn and verify about each other's keys before they establish the secure channel. So far, communication providers have given users two mechanisms to establish trust. The first mechanism is out-of-band trust establishment. As the name suggests, this means that users need to meet in person or otherwise communicate out of band to exchange keys and verify that they are seeing the right keys for each other. But verifying keys out of band requires users to reason about encryption and keys, and there are many studies showing that this is an unintuitive and error-prone process for the vast majority of people. Several large secure messaging providers have decided to automate trust establishment for their users by handling key management completely on their behalf. But is this approach actually better? These providers handle key management entirely in the background, maintaining a database of all of their users' keys. So all Bob needs to do, if he wants to communicate with Alice, is query the provider for Alice's client, for Alice's key, sorry. And I should say that it's Bob's client that's doing this, not Bob, the person. This way, Bob doesn't need to worry about or even see encryption keys. But there is a caveat to this system, and that is that Alice and Bob must trust the provider unconditionally because they can only assume that their clients are receiving the right keys. But the secure messaging provider could be compromised by a malicious insider and issue fake keys for its users. Then, even if client A registers Alice's legitimate public key, the compromised provider equivocates, presenting Bob's client a different key for Alice, one that it controls. Since the provider routes all of its users' messages and any communication from Bob to Alice will use the fake key, the equivocation attack allows the provider to be a man in the middle and to decrypt and read all of Bob's encrypted messages. So in summary, weighing the two existing trust establishment methods against each other, out-of-band trust establishment provides strong security since users can really be sure that they are establishing a secure channel with the person that they expect. But the usability of this method does leave a lot to be desired since it's a very unintuitive process for users. On the other hand, having communication providers establish trust on behalf of their users is less secure because it does leave them vulnerable to equivocation attacks, but it is much better in terms of usability since users can remain agnostic to the encryption. What we really want is a system that will allow users to establish trust securely without sacrificing usability. So how can we get the best of both worlds? Well, the ideal trust establishment method will provide security against equivocation attacks and also be automated, meaning that users don't need to worry about establishing trust in the first place. We think the reason that the existing approaches aren't able to provide both of these properties is because they verify the correctness of keys. In other words, what users really are verifying is that an encryption key bound to an online name, like alice@mail.com, is in fact controlled by a real-world person called Alice. We believe that the main problem of verifying correctness is that it requires users to communicate out of band, since this is the only way they'll be able to establish the link between the real-world person and the online name-to-key binding. We think these issues can be addressed by changing what it is that clients need to verify to establish trust. Our approach is to verify the consistency of keys instead of correctness. And by consistency, I mean that a user's key doesn't change unexpectedly over time, and that all clients see the same key bound to a given name. The main advantage of checking consistency is that it's possible to enforce it over time and across clients using various cryptographic constructions that I will go into in a moment. But the idea is that providers manage their users' consistent keys in a verifiable key directory, resulting in an automated key verification process. We use this approach of consistent keys to design and build CONIKS, a key verification system for end-user public keys. It enables automated trust establishment without having to trust the communication service provider unconditionally. And again, this is because identity providers maintain consistent bindings from names to keys. Software clients in CONIKS then verify the consistency of their contacts as well as their own users' bindings. And the goal really is to make equivocation attacks efficiently and promptly detectable. Let me give you an overview of a typical CONIKS system. The main players are the identity provider and the clients, which perform the consistency checks on the behalf of their user. For simplicity, I'm only showing a single provider here, but our system is designed to work as a federated system of many providers that are separate and independent but can communicate with each other, kind of like email providers today that they can talk to each other, but they have their own user bases. So much like in existing secure messaging applications, the first step involves client A registering a mapping from Alice's name to a public key with the provider. Then when Bob wants to send Alice a secure message, his client looks up her public key at the provider, and this will be Alice's public key. Client B verifies the consistency of PKA and encrypts Bob's message to Alice using PKA if the consistency checks pass. Now for this to work seamlessly, Alice and Bob must be confident that both of their clients are seeing consistent bindings and that neither of their public keys has changed unexpectedly. But as we saw earlier, the provider could be malicious and present client B a different key for Alice. So how might clients check the consistency of their name-to-key bindings? In a Strawman design with a single provider and 4 clients, each client could periodically download the entire key directory and check that the key in each individual binding remains consistent over time. Then to check that all clients are seeing the same keys, each client exchanges and compares its version of the key directory with every other client. This way, all clients can be sure that all bindings in the provider's key directory are consistent. But this is very wasteful in terms of bandwidth and storage. So our design for CONIKS focuses on making consistency checks more efficient. We achieve this by having identity providers generate directory summaries, so clients don't have to verify all of the bindings to check for consistency. To compute these summaries efficiently, providers store the bindings for their users in Merkle prefix trees. Merkle trees in general give us the nice property that the root node is the summary of all of the bindings stored in the leaf nodes, because each node in the tree contains the hash of the subtrees below it. This means that the directories that providers maintain are tamper evident because any change to one of the bindings in the leaves will result in a change in the value of the root. And the tree roots are digitally signed by the provider that generates them, so they serve as an undeniable statement about the contents of the tree at a specific point in time. So these summaries I'm talking about are really just the signed tree roots, or STRs. CONIKS then uses Merkle trees and the signed tree roots to provide two main security properties for name-to-key bindings. First, there must not be any unexpected key changes. In other words, the expected key in a binding must be included in the signed tree root. And the directory must have non-equivocation, which means that all clients must see the same signed tree root. So you might notice here that these security properties correspond to the consistency properties I introduced earlier. This is because ensuring consistency is really what is allowing CONIKS to provide security. I'll explain briefly why we need to ensure each of these properties and how CONIKS does this. So why do we need to ensure that an expected binding is included in the signed tree root? The reason is that if providers don't prove this property, clients have no way of detecting fake keys that a provider inserts into the tree after generating the signed tree root. Because the signed tree root really acts as a sort of commitment to the contents of the tree. So providers need to prove that name-to-key bindings are included in the signed tree root in order to generate evidence for fake keys. CONIKS uses Merkle authentication paths as proofs of inclusion. For those of you who might be less familiar with Merkle trees, an authentication path is a pruned Merkle tree that only contains the nodes along the path from the specific binding to the root, and it preserves the hashes of the subtrees that were pruned away. Clients verify an authentication path by recomputing the root node of the tree. And they check then that this recomputed root node is consistent with the signed tree root. And I just want to point out here that checking for unexpected key changes requires clients only to download data sizes on the order of big O of log n for a tree with n bindings in CONIKS, compared to the Strawman that required linear, or data like on the order of big O of n, sorry. At a high level, clients check that a specific binding is included in the signed tree root as part of key lookups. So when client B queries the identity provider for Alice's key, the provider returns her key pKa, the authentication path to prove inclusion, as well as the signed tree root. To check that the return key hasn't changed, the client compares the returned pKa to the previous version of the key that the client retrieved. Client B also verifies the authentication path by recomputing the root of the tree and verifies the signature on the signed tree root using the recomputed root from the authentication path. And one important thing to note is that client B will perform the same checks for Bob's key on a regular basis. And this is to make sure that the provider is also including Bob's expected binding in its signed tree roots. The second property CONIKS needs to provide is non-equivocation, meaning that all clients see the same signed tree root for a given provider. Why do we need this security property? I already talked a bit about this earlier. If the provider is able to present different clients' diverging views of its key directory, the client can become a man in the middle and impersonate users. So providers need to prove non-equivocation to allow clients to detect attempts by the provider to act as a man in the middle. Since the views of key directories in CONIKS are represented as signed tree roots, CONIKS ensures non-equivocation using these signed tree roots. Just to give you an idea of how signed tree roots actually look like, if you take the current version of a Merkle tree, the provider computes all the hashes, generates the root, which become part of the next signed tree root. And this then allows the providers to generate a verifiable history of these signed tree roots. This history is built in the form of a hash chain of signed tree roots, meaning that each one must also include the hash of the previous STR in the next signed tree root it generates. or the provider generates. The idea is then that the hash chain serves as a commitment to all of the signed tree roots ever generated by the provider. Clients verify the hash chain by checking that the hash of the previous root is then included in the next one. But just checking that the hash chain is properly constructed isn't enough to provide non-equivocation. And here's why. Let's assume that the provider is presenting client A this linear hash chain of signed tree roots. Client A will verify this hash chain is valid since, again, the hash of each prior signed tree root is properly included in the more recent one. However, the provider could be malicious and present client B a different, yet also valid version of its STR history, meaning that the provider has equivocated and created a fork in its STR history. So if clients A and B never see the other's branch of the hash chain, they won't detect the attack. For this reason, identity providers in CONIKS cross-verify each other and collaborate with clients to ensure non-equivocation. The provider with the star here is the one that's going to be verified in this example. But anyways, the way checking for non-equivocation works is that whenever the starred provider generates a new signed tree root, it publishes this to the other identity providers in the system. These verify the hash chain, as I explained before. And then at some later point in time, when client B wants to check for non-equivocation, it chooses other identity providers in the system at random, and in this case, it'll choose the one on the left and on the right, and queries them for their view of the starred identity provider's signed tree root. Client B also retrieves the signed tree root from the starred provider and verifies the hash chain for this STR. Lastly, the client compares the different views to check that they are consistent with each other. If they are, the client can be relatively confident that the provider isn't equivocating. But client B can also repeat this protocol with additional other providers to increase its confidence. Now I want to switch gears to talk about privacy. Unfortunately, in the interest of time, I won't really be able to go into great detail here, but I do want to point out the privacy challenges that we faced in CONIKS. So we certainly don't want to publish a large list of the usernames for all of a provider's users. This challenge is already largely addressed in CONIKS by the fact that clients checking the consistency of bindings only need authentication paths and signed tree roots to do so. But even with authentication paths, we found that an attacker can still infer information about other users based on a given authentication path. So this is one of the challenges that we address in CONIKS. We also face the issue that we don't want CONIKS to publish the public keys associated with the usernames in a key directory. And we might not even want to expose the total number of users with bindings in a provider's directory. Again, in the interest of time, unfortunately, I won't be able to talk more about privacy in CONIKS, but it was important to us that our design be compatible with the privacy requirements of, say, a Google or a Yahoo. So we did address each of these challenges using some crypto tricks that are practical for an end-user secure communication system. But we describe our solutions to these challenges in the paper. Finally, to demonstrate the practicality of CONIKS, we wanted to answer these questions about our performance. Does our server design scale to the size of a typical user base of today's communication service providers? And in particular, does our design scale to thousands, millions, or even billions of users? At the same time, on the client side, are the CONIKS consistency checks that clients need to run on a frequent basis efficient enough to run on today's mobile devices? And we also wanted to know if CONIKS integrates well with existing end-to-end secure communication services. We sought to answer these questions by making real and theoretical measurements using a prototype CONIKS server and a prototype client. The highlights of our evaluation are the fact that our server prototype scales to tens of millions of users on a single commodity machine. And in particular, our prototype is able to process 1,000 insertions to the tree with 10 million users in 2.6 milliseconds, which we don't think will or would place a significant burden on communication service providers today. On the client side, our consistency checks are efficient enough to be run on today's mobile devices, needing only a little extra bandwidth and storage. For example, the maximum bandwidth requirement to perform a consistency check is less than 20 kilobytes per day, and only a small fraction of this downloaded data actually needs to be stored on the device. And finally, we built a proof of concept secure chat client to evaluate whether CONIKS does integrate well with existing secure messaging services. In particular, we integrated CONIKS into the off-the-record or OTR plugin for the Pigeon IM client and found that the consistency checks fit well into the workflow of this application. And again, for a more detailed discussion of our performance and our proof of concept, please see our paper. To conclude, the main idea behind our work is that users shouldn't have to worry about managing keys and establishing trust securely. But secure communication service providers also shouldn't be trusted to behave properly and always act in the interests of their users. The main principle in CONIKS is to provide strong security through consistency, which might be a slightly weaker property than correctness, but we think it's much more practical to automate. And we're excited that Google and Yahoo are in the process of adopting CONIKS in their end-to-end secure communication applications because we're hoping to learn much from seeing our system in the wild. For more information, we also have a website. Our reference implementation of our prototypes is on GitHub, and we'd like to thank the engineers that we've been working with so far. And I'm happy to take questions.
So the attack that the provider can do against Alice to make Bob think Alice has the wrong key isn't necessarily just to change Alice's key, but to say, oh yeah, Alice has an additional device. It's the FBI key's device. It's the device of the FBI key. And then Bob's client would encrypt to both keys. Alice gets the message just fine, but also there's an extra one. So how can Alice's device, when checking the CONIKS server, know whether or not Alice has a travel laptop in her bag that she turns on twice a year?
Yeah, so we didn't quite address the multiple device problem, which is something that we definitely would like to do in the future. We sort of imagined that devices could authenticate each other. So if Alice has sort of a primary device, her primary device could, say, sign the keys for other devices, and if it detects a new one, it could sort of raise a flag and alert Alice. So we're sort of imagining something along those lines.
That's not addressed in this work.
Right.
Okay.
Hi, nice work.
Thanks.
I wanted to know what happens when a user's key is compromised and they need to change the key and that will lead to inconsistency, and what happens if I want to deny service and so I claim that I saw your key as something else so that your client will see an inconsistent state?
So the first part of your question is about key change, right? We haven't, let's see, so we thought more about, sorry, let me back up. We did think about key change a lot, and I guess there are two parts to the key change problem. One thing is like how clients even change keys in general. And I think the other part of your question was more like what happens once an inconsistency is found, how they recover from that.
Well, the other question, so the first question was, you have inconsistency for legitimate reasons. I had to change my key.
Yes.
The second question is, you have inconsistency for malicious reasons.
Yep.
I don't want you and Bob to communicate. So I'm going to claim to Bob that I saw a key that wasn't your key, so that your client sees an inconsistent state, and now it has to either pop up an error message asking you what to do, and we're back to the user making a decision, or you need some algorithm to figure out what's going on there.
Yeah. So these two cases should be handled differently, and it's like pretty nuanced. So maybe we should talk about this offline. But I think in general, the denial of service, like presenting a different key. Hopefully, if other clients are checking sort of non-equivocation with like other providers, they should be able to detect the inconsistent tree roots or the summaries of the directory, right? So they should at least be able to see that something weird is happening. But yeah, I think, I'm not sure if I'm answering your question very well, but I think the only device that could detect the denial of service would really be the client being attacked, if that makes sense. Sorry, yeah, we should talk offline about this.
Thanks for the talk, Albert Kwan. So I had a similar, I guess a related question to that.
Mm-hmm.
So is there a way to handle key revocation in your system? So if it gets compromised, I want it out of the system, but Merkle trees don't handle proof of exclusion really well, right? So I was wondering if you have any ways.
Yeah, so I guess we consider revocation sort of in the sense of key changes again. Yeah. The way we can handle this, it'll depend kind of on user settings and stuff like that. I didn't go into this at all, but we do talk about it in the paper.
Okay.
But the general idea would be to have the client sort of take the old key and sign it with a new key, or sorry, the other way around, sign the new key with the old key to sort of prove that it owned the old key and it's authorizing this transition. So I guess it's not really a revocation in the sort of certificate sense that you take that off, but it does prove sort of the authorized change. But yeah, we can talk about it more also.
Thanks.
Hey, Alessandro Di Federico from Politecnico di Milano. So, but what if, let's suppose that Alice is not in your system, but someone subscribes as Alice? Mm-hmm. Then if people start to think that actually Alice is on the system, they will start, to trust her and these kind of things. But if you never check its identity out of band, if you never go to Alice and ask it, but are you actually on that system, or if you never ask a secret question, as it happens with the socialist millionaire problem, in OTR, in the current OTR implementation, how can I be sure that it's actually Alice and it's not someone else?
Yeah, so we think that sort of establishing the link between the real world person and the online identity is, it's definitely an important problem that we haven't solved. But we imagine that this will sort of happen naturally in the way that it sort of happens already, because normally, today we learn each other's online identities by talking to each other, meeting in person, exchanging business cards, that sort of thing. So it's not a really elegant solution, but we imagine that people will bootstrap sort of in ways that they already are used to. Might be a little different for sort of closed systems like iMessage, where you don't even know what the other person's phone number is or whatever, but
That's it. Thank you.
Okay, let's thank our speaker one more time.